Hello, in this video we continue to explore the possibilities of work with your data using MDAnalysis library. Whereas my previous video was about topologies, this one is about trajectories. There are multiple trajectory formats that depend on the molecular dynamics package, but they all have a common structure. They contain coordinates of your atoms, sometimes velocities and forces, if you decided to preserve those, and also box dimensions. They usually don't have definitions of atoms, as it is highly inefficient to store those alongside each frame, so you usually use trajectory files in a pair with file with topological parameters. But there are exceptions like PDB file, which can contain multiple models, and it's like a trajectory, highly inefficient trajectory. You can manipulate trajectories in different ways using MDAnalysis library. You can slice them into pieces using frame indexes. You can combine them back together. You can load multiple trajectories into one universe. You can load multiple universes. You can perform various comparisons of structures in each frame of trajectories using different tools stored in analysis module of MDAnalysis library. Convert between different trajectory formats. You can write your trajectories obtained during work with MDAnalysis library into different file formats, storing it on your SSD, but you can also serialize them as binary representations using Pickle, which is supported by MDAnalysis library, most of its data structures, but it is more like an advanced developer feature, I imagine. Now I will show you how to slice your trajectory, convert between different file formats, and save only those parts of your system that you want per each frame. As always, we start by creating a universe instance, and we can check the number of frames loaded from our trajectory. A total of 7,501 frame. To split my trajectory into 3 different parts of equal lengths, I will define a splitting point, which is exactly at 2,500 frames, and I will just move about my trajectory by scaling this splitting point. There are two ways how you can write your trajectories into SSD, which is slightly more involved than working with topologies, and in both cases you create atom group with exactly those atoms that you want to preserve per frame of your trajectory. I will first store my protein atoms by selecting them from universe. The first way is the easiest one. You just use write method like you would do with your topologies, but you define that you want to preserve certain frames of your trajectory, not just one frame, and you define which exactly frames you want to preserve. Specifically, you use frames keyword, and you pass as a value your trajectory, and specific frames you select by using fancy indexing with your splitting point. And I will repeat this with all my remaining 2 parts of trajectory by just shifting indexes. demonstrate one of the resulting trajectory pieces. It is exactly 2500 frames from the beginning of my trajectory. Only 2 protein chains are preserved from my universe. As for the second way to write down your trajectories, you can use the writer class of MDAnalysis library. In this case, I will select C-alpha carbons for the sake of diversity. You would usually select either C-alphas or backbone atoms of your amino acid residues to perform RMSD analysis. The most idiomatic way to use writer class is by using it with context manager, which will automatically handle opening and closing file for you. It is more involved as you have to iterate over each frame and decide whether you want to write, but it also gives you more control on the writing process. For example, you can select frames only with specific indexes, not just by using slicing of your trajectories or by applying some other conditions with logical operators. It is very cool because most of the tools of molecular dynamics packages that work with trajectories like TrajectConv or Gromax package, they only allow you to a certain extent configure transformations of your trajectories by passing command line arguments, whereas MDAnalysis library can be tuned to your specific workflow. Also, you can write your data in almost all existing trajectory formats. This time I decided to store them as protein databank files to exactly show you how you can store your trajectories in probably the most inefficient way possible. Here I receive a bunch of warnings because certain parameters were not specified in my topological file, which is 0 file, and it is actually quite common because 0 file contains much less data on your structures than a protein databank file. I must warn you though that by storing your trajectory frames as separate models in protein databank files, you may encounter a problem regarding the hard limit of legacy PDB, which is it can store up to 100,000 atoms because the atom index field is limited to 5 characters only. Although legacy PDB is still widespread and will probably remain there forever, but we now have newer file format exactly to handle the cases with large systems, which is a PDB PMCID file format. But it is mostly due to the cryo-electron microscopy capabilities rather than specifically related to molecular dynamics simulations cases. However, we can also make use of it in MD field. In dynamics, you can notice that only those atoms that are in the outer part of our structure and not in the globular are moving actively, whereas those in the globular, they are largely restrained by steric conditions. I have now switched to sphere representation of C-alphas. Now I will show you how to load our trajectory in slices. With multiple trajectory slices, we still need to provide file with topological parameters, definitions of all atoms, which is in this case protein GRO file. Multiple trajectories can be loaded either by providing them as one list or by specifying them as multiple arcs in the universe interface after file with topological parameters. Verify that everything is loading correctly. Let's run the MSD calculations using C alphas this time instead of backbone atoms. Everything is fine, and as you can see, all three pieces of our trajectory were loaded together, resulting in a final full length of trajectory. If we remove just one of the passes, we will obtain a shorter trajectory with only 200 nanoseconds instead of 300. As I said, it is not strictly required to provide your passes as list. You can just provide them one by one as arguments directly. That's all for today. Thank you for watching, and as always, you can ask your questions in the comment section.